Hi viewers, welcome back. This lecture is about Module 3 on Electrical Fundamentals, Sub-Module 7 on Resistance. We will be uploading videos on each and every topic, so if you have not subscribed our channel, then please subscribe and also press the bell icon so that you never miss any updates from your channel. Ohm's law states that the current in a wire is proportional to the potential difference between its ends. Thus, current is directly proportional to voltage across the conductor. The ratio of voltage to current is known as resistance. Unit of resistance is ohm, sign is omega, and 1 ohm is equals to 1 volt per ampere. Resistance of a conductor. The resistance of a metallic conductor is directly proportional to its length. It means that the longer the length of a given size of wire, the greater the resistance. The resistance of a metallic conductor is inversely proportional to the cross-sectional area. It means if the cross-sectional area of a conductor is doubled, the resistance to current flow will be reduced. And the constant rho is known as resistivity. It is the characteristics of the material. Resistivity has a symbol rho. It is defined as the resistance between the ends of a piece of material 1 meter long which has a cross-sectional area of 1 square meters. Unit of resistivity is ohm meter. The resistivity of metal such as copper is minimum 1.7 multiplied by 10 raised to the power minus 8 ohm meter. For semiconductor such as silicon, it is high 2.3 into 10 raised to the power 3 ohm meter, and for insulators it is the highest like quartz 5 into 10 raised to the power 16 ohm meter. Variation of resistance with temperature. The three factors which affect the resistance are length of a conductor, area of a conductor, and the type of conductor material. The fourth major factor influencing the resistance of a conductor is temperature. The resistance of all materials depends on temperature. With increasing temperature, the atoms vibrate more rapidly. The electrons moving through a metal make more collisions, effectively making the resistance higher. The resistance of all pure metal increases with temperature, whereas the resistance of electrolytes, insulators, carbon, and semiconductors decreases with increasing temperatures. Experimentally, if we take a piece of pure metal and make its temperature 0 degrees Celsius by means of ice and then increase its temperature gradually from 0 degrees Celsius to 100 degrees Celsius by heating it, then if we plot resistance versus temperature graph, we will observe that resistance of the metal piece is gradually increased with increase in temperature. We will get a straight line for resistance versus temperature graph. If this straight line is extended behind the resistance axis towards left, it will cut the temperature axis at some temperature, suppose minus T0 degrees Celsius. At this temperature, the electrical resistance of the metal becomes 0, and this temperature is referred as zero resistance temperature. Suppose R1 and R2 are the measured resistances at temperature T1 degrees centigrade and T2 degrees centigrade respectively. Then we can write the equation as As we know, resistance is directly proportional to temperature. So R1 is directly proportional to T1 plus T0 and R2 is directly proportional to T2 plus T0. So if we take ratio of R2 upon R1, this will become R2 upon R1 is equals to T0 plus T2 divided by T0 plus T1. As they were in proportionate, and if we will make them in ratio, the constant quantities will cancel out. And this will be the simplest expression which we will get for the variation of resistance with temperature. This relation will help us to determine the temperature coefficient of resistance. The temperature coefficient of resistance measures changes in the electrical resistance of any substance per degree of temperature change. Let's consider a conductor having a resistance of R0 at 0 degrees centigrade and RT at T0 degrees centigrade respectively. If we take the ratio which we have taken earlier, RT divided by R0 equals to T0 plus T divided by T0 plus 0 degrees Celsius. So RT is equals to, if we will take R0 towards the right hand side, then it will become RT is equals to R0 plus R0 multiplied by T divided by T0. Then again if we will take R0 towards left, then RT minus R0, this is difference of resistance, that is change in resistance, and this will equals to R0 T divided by T naught. And 1 upon T naught is known as alpha naught. It is the temperature coefficient of resistance of that substance at 0 degree Celsius. So del R will become alpha naught R naught T. Thus, change in resistance, which is del R, of any substance due to temperature mainly depends upon three factors. First, the value of resistance at initial temperature. So here at initial temperature it is R naught. The rise of temperature, which is T. And third, the temperature coefficient of resistance, which is alpha naught, and where alpha naught is equals to 1 upon T naught. Materials whose resistance increases with increasing temperature have positive temperature coefficient of resistance, and material whose resistance decreases with increasing temperature have a negative temperature coefficient of resistance. So we are continuing with the previous relation, that is del R, which is equals to RT minus R naught is equals to alpha naught R naught T, where alpha is equals to temperature coefficient of resistance and which is 1 upon T naught. So if we will make this equation RT minus R naught, which is directly proportional to R naught, T2 minus T1. So RT minus R naught, if we will remove the proportionate signal, it will become alpha times of R naught T2 minus T1. And if from left hand side, if we will take the R naught towards the right hand side, then R naught is common. So our final equation will become RT is equals to R naught multiply by 1 plus alpha T2 minus alpha T1. This equation is important. This gives the change of resistance with increase in temperature. Similarly, if we will write in terms of rho, resistivity, this equation will become rho T is equals to rho naught complete multiply by 1 plus alpha T minus alpha T naught. The electrical component used to introduce resistance into a circuit is called a resistor. Resistors can be linear or non-linear. Linear resistors can be fixed or variable. Resistors are shown with different symbols which are used in circuit diagrams. The old and new symbols are shown here for your reference. Color codes. The current method of color code making of resistance is the band system. Here we have been given 6 band system. Band number 1, 2 and 3 give the first 3 numbers of the resistor value. Band number 4 gives the multiplication factors, which is the number of zeros. The 5th band gives the tolerance. Tolerance indicates how close the actual value may be to the stated value. And the 6th band gives the temperature coefficient. So here the first digit is 5, the second digit is 6, the third digit is 0. So 560 is the numerical value of a resistor. Fourth digit gives multiplier and here it is 1k, that is 10 raised to the power 3. Fifth gives tolerance, which is decimal 1%. And the sixth gives temperature coefficient, which is 50 ppm per degree centigrade. Sometimes resistors have 4 bands. In that case, first 2 bands gives the number of resistor value, third band gives multiplication factor, and the fourth band gives the tolerance value. Potentiometer. The potentiometer is considered a 3-terminal device. As shown, terminals 1 and 2 have the entire value of the potentiometer resistance between them. Terminal 3 is the viper or moving contact. Through this moving contact, the resistance between terminal 1 and 2 can be varied. The potentiometer is used to vary the voltage in a circuit. A typical use potentiometer can be found in the volume controls on an audio panel and input devices for flight data recorders in aircraft. Rheostats. A rheostat is a variable resistor used to vary the amount of current flowing in a circuit. As the slider arms moves from point A to B, the amount of rheostat resistance, which is AB, is increased. Since the rheostat resistance and the fixed resistance are in series, the total resistance in the circuit also increases and the current in the circuit decreases. On the other hand, if the slider arm is moved towards point A, the total resistance decreases and the current in the circuit increases. Voltage division. Series circuit has a simple path to pass current. The same current is flowing through each component or load, but voltage drop across the series resistance. Thus, V1 is equals to I times of R1 and V2 is equals to I times of R2. V1 is voltage across resistance R1 and V2 is voltage across resistance R2. V1 plus V2 is equals to the supply voltage, which is Vin. Thus, V1 is directly proportional to R1. So, if resistance value of R1 is increased, the voltage drop across this resistance will also increase. And V2 is directly proportional to R2. If we know the value of R1 and R2, we can find out the voltage drop across each resistors. Voltages related to earth. The earth is a reference point and considered to be at 0 volts. Potential differences between earth and the negative terminal of the supply result in negative voltages, and potential differences between earth and the positive terminal results in a positive voltages. If we will see the example towards the left, the circuit have been provided a source voltage of 40 volt. There are three resistors towards right, and there is a voltage drop across these three. So if we add all these three voltages, that is plus 36 volt, plus 12 volt, and minus 4 volt, it comes out to be 40 volt. So in a series circuit, voltage is additive. This we have proved. Now second thing, if we will see the resistor across the first resistor, the top resistor, it is 36 volt. If we will see the middle one, it is reference one end is at 0 volt. It is connected to earth. So earth means 0 volt. And the upper one is showing 12 volts. So it means that the voltage drop across the middle resistor is 12 volt. And as the middle one is one end is connected to earth, so if we'll go further down, the third resistor is having one end at 0 volt, which is at earth, and the other end is connected to the negative to the input supply. So here the voltage drop across the third resistor will be negative, and it is shown here as minus 4 volt. Current dividers. Current divider circuits have two or more parallel branches for current to flow through, but the voltage is same for all components in the parallel circuit. So voltage across R1 is equals to V is equals to I1 R1, and voltage across R2 resistance is equals to V is equals to I2 R2. Applying Ohm's law, the voltage source, which is V, is equals to I times of total resistance. So if we want to calculate the current in the resistance R1, which is I1, is equals to V divided by R1. And we know that voltage is equals to total current multiplied by total resistance. So we'll simply write I multiplied by R total and divided by R1. So we got IR1 is equals to total current, which is I or IT, is equals to multiplied by R2 divided by R1 plus R2. R total is the total resistance, and we know that for a parallel circuit it is R1 R2 divided by R1 plus R2. So R1 is in denominator and R1 R2 is in numerator. So R1 get cancels. The final equation will be IR1 is equals to IT multiplied by R2 divided by R1 plus R2. The Wheatstone bridge. This bridge is a useful electric wiring circuit constructed of three resistors with known values R1, R2 and R3, and a voltmeter connected between terminals C and D, which is V out, and a fourth resistor, which is R4. Unknown value is included and is shown in the figure. When the circuit is wired as shown, the voltage values at C and D vary with total resistance on each side of the bridge. The ratio of R1 by R2 is equals to R3 divided by Rx or R4 will be equals to 1 when this bridge is balanced. Balanced means the voltmeter which is connected between terminal C and D will read 0 volts. To find the unknown value of resistance R4, we will use the same equation, and R4 or Rx will become R3 multiplied by R2 divided by R1. And similar way, we will find out the voltages across node C and node D, which is the voltage across resistance R2 and voltage across resistance R4. And V out will be VC minus VD. While varying the resistance values, if we find that V out is equals to 0, so at that time we will consider this Wheatstone bridge to be balanced. The Wheatstone bridge is useful for measuring and displaying remote indications. On aircraft, Wheatstone bridge circuits are used for the measurement and display of temperature, pressure, position, and quantities. So we have reached to the end of this session. If you found this video interesting, then please like the video and share it with your friends, and don't forget to subscribe. Thanks for watching.
Thank you.